Our next speaker is Barbara Kraus from the University of Innsbruck, who will be telling us about some aspects of quantum computing and its verification. So please, Barbara, the floor is yours.
Thank you, Dara, very much. If you can see my screen. So hello, everybody from Innsbruck. I would like to thank also very much the organizers for setting up this meeting. And what I would like to talk about are some aspects of quantum computing and a little bit about the verification thereof. So what I would like to consider in this talk is a so-called circuit model, where we have n qubits that are initially prepared in some computational basis state, for instance, all in 0. And we are applying a set of gates in order to process quantum information. And afterwards, we make some measurement in order to obtain the outcome. Now, if we think, or if you look at something like this, then there are some obvious questions that present themselves. Namely, we want to know whether such a computation is classically efficiently simulatable. So is it actually doing something that I could also do on a classical computer? Or is it actually something that I can probably not do on a classical computer efficiently because it's something with which I can do universal quantum computation? And if this is the case, then what becomes more and more relevant these days is to find also ways of how we can verify that. Okay, so I mentioned that I can do here really some computation that I cannot classically efficiently simulate. Then how should I know whether the outcome that I obtain here is the correct one? Okay, so these are interesting questions in this context, and these are the questions that I would like to address in this talk. And one gate set that is very well suited for that are the so-called match gates. So I will explain in a second what match gates are. But these are simply some 2-qubit gates that have to obey some algebraic constraints. And match gate circuits are just circuits that are just using this kind of gates. Another interesting thing about these match gates is that on the one hand, they are classically efficiently simulatable. So if you have a circuit where you only apply these kind of gates, then the output that you obtain here, you can also obtain it on a classical computer efficiently. Okay. Furthermore, for these match gates, you can show that not only can you simulate them classically efficiently, but actually you can compress them into an exponentially smaller quantum computer. And so what I mean is that if I have here a computation that is consisting only of match gates and it's running on n qubits, then I can carry out exactly the same computation on an exponentially smaller computer, so just having log n qubits in basically the same time and obtaining the same outcome. Okay, so the interesting thing here, of course, is that, I mean, first of all, if I can compress a computation, then my Hilbert space is now a Hilbert space of log n qubits, means that it's linear in n. Hence, if the computation here is polynomial, then I have to apply polynomially many gates on log n qubits, which means that I have to multiply polynomially many n times n matrices, which of course I can do efficiently classically. Right? So whatever could possibly be compressed into an exponentially smaller quantum computer has to be classically efficiently computable as a function of this large system, okay? Not as a function of the small system, of course. So there is some important thing that I'm hiding in this arrow, which is the compression. So the way that I do this mapping from the large quantum computer to the small quantum computer, because this is using some classical computation. And the important thing here is that the classical computer that you're allowed to use here is restricted in space. It's restricted into polylog n, so that the classical computer that does the mapping cannot do the computation. So it cannot carry out the computation. Stated differently, the computation that I want to simulate, that is run on this n qubits, is now performed on these log n qubits. Okay, it's really the quantum computer that does this computation. Okay, this is a very old result together with Richard Josaki, Masami and John Watrous. And what we did recently, or relatively recently, is to use that actually to simulate, for instance, a compressed quantum simulation of an Ising model. Okay, so you can, for instance, obtain then in a compressed way, you can observe quantum phase transitions and so on, which means that you really use now a very small quantum computer to observe the quantum phase transition of a very large system. And we also did that, we realized it, for instance, with the IBM quantum computer. So this is telling us that match gates, these kind of special gates that I still didn't explain what they are, but they are kind of really special because you can even compress the computation into something that is exponentially smaller. Okay, so this gives the impression that they are not very powerful, right? So on the one hand, they are classically efficiently simulatable. On the other hand, you can even compress it. So it seems that, okay, you cannot do much with these match gates. So this is why I would like to ask now the kind of opposite question, namely, can I go from something like that is not very powerful because it's even compressible? Can I add something to that, some resource, in order to make this computation universal? Okay, and this is, you want to know what kind of gates or what kind of additional resources can you add to make this computation universal so that you can then do any kind of quantum computation on that device. And this is the question that I would like to address. And the reason for that is that, of course, it's interesting from a fundamental point of view. It's also interesting because we learn more about computational simulation of computational models. But on the other hand, you can also use this kind of idea in order to find some ways of testing your quantum device. This is what I will tell you about at the end of the talk. But let me first start out explaining briefly what are match gates. These are simply 2-qubit gates that are direct sum of single cube of 2 times 2 unitary matrices, which have to obey the condition that the determinants match. Okay, so this take a different way is just a direct sum of a unitary acting on the even parity subspace plus one that acts on the odd parity subspace. And if you look, for instance, at this example of a swap gate, then you see that it does have this structure of this gate, but the determinants don't match. So this means that the swap gate is not a match gate. On the contrary, actually, it has been shown many years ago that if you would add the swap gates to the set of match gates, then you have a universal quantum, universal gate set. Okay, so you could do any kind of quantum computation. So swap is not an element of this match gate, and this is important and will be important also later on. But everything else that is of this form are match gates, and you see in contrast to, for instance, the Clifford gates that you really have here 3 parameters. Okay, so this is not a finite gate set, but you have really continuous variables here, continuous parameters here. And so a match gate circuit is now simply a circuit which starts out with all qubits being prepared in the computational basis state, and then you apply these 2-qubit match gates always on nearest neighbors. Okay, so these are only acting on nearest neighbors, as you can see here, which is also important. And at the end, you make a measurement of a single qubit here in the set basis. And if you do so, then, as I said before, you can simulate this whole computation classically efficiently. And furthermore, you can actually compress it into an exponentially smaller quantum computer. And so the question that we want to address now is, okay, so what do I have to add to such a computation in order to make it universal? And so the main idea is that you have this gate set that is efficiently simulatable, and you want to add some so-called resourceful gates in order to have a universal gate set. Okay, so the gates that I'm allowed to use, this is my free resource. In this case, this will be our match gates. They are free. I can use them for free. And I want to add some additional gates in order to get a universal gate set. Okay, and there are several examples known. But instead of doing that, what you would like to do is not to really add some additional gates, but you want to do that in a different way. And let me explain that with the help of Clifford gates. So Clifford gates, as many of you probably know, is another gate set that can be simulated classically efficiently. They're here, these are just the operators that leave the Pauli group invariant. And it is well known that if you add to the Clifford gates the so-called T gate, which is just a phase gate with a phase pi/4, then you get a universal gate set. Okay, now instead of adding this T gate, so instead of having to apply it on different places in the circuit, what I would like to do instead, or what has been shown many years ago, is that you can use a single qubit state, the so-called T state, that is of this form. And if you want to apply a T gate on that system here, in whatever state it is, then you can entangle it to your auxiliary state. You make a measurement of this auxiliary system, and depending on the outcome, you apply either the identity or sigma set. Okay, in this way, you can show that you can deterministically realize this transformation. So you have deterministically implemented now this T gate. Okay, which is very nice because this means that I just need, in this case, Clifford gates plus these T states and adaptive measurement in order to get universal quantum computation. Okay, so I could simply prepare many of these states, do adaptive measurements whenever I need it, and then I have a universal quantum computer. So now we would like to do something similar for the match gates. But we are facing here actually a very big problem because, as I mentioned before, the swap gate is not a match gate. Okay, so this means now what? This means that even if I would come up with some states that I could use in order to realize, to implement some resourceful gate here denoted by V, then I could realize that here, so I could apply this V-gate to this next qubit that is next to my auxiliary state here, but I could not do it here, because how can I map this state here next to the qubit that is here? Okay, so I cannot easily do that because the swap is not contained in my free gate set. Okay, so I cannot use the swap gate to do that. Okay, so this is why the situation here changes completely compared to the Clifford gates. So the question is, do these actually exist? And in fact, many years ago, Sergei Bravi already showed with an example that such a state does exist. What we showed, and this is together with Richard Choser, Martin Hevenstein, and Sergei Strelchuk and Mitterner, what we showed is that actually any pure fermionic non-Gaussian state is a magic state for match-gate computation. So what does this mean now? Fermionic mathematically simply means that it's an eigenstate of sigma zeta and so on. So it's has a fixed parity. And non-Gaussian means that you cannot create it with free operation. So the state cannot be generated by just using match gates. Okay? So fermionic means basically that you can transform the state to any state where you need it, so where you need to apply a swap operation. So for this, it has to be fermionic. Actually, you can show that this is a necessary condition. And non-Gaussian means that it's not for free. Okay? So actually, the pure fermionic non-Gaussian states are is the largest set of states which could possibly be a magic state for match-gate computation. What you can show is that indeed, all these states can be used for match-gate computation. A simple example would be this one, which I wrote down here, which is just 2 copies of the maximal entangled phi plus state. If you have this state and you allow for adaptive measurements, then you can realize the swap gate deterministically, and hence you have universal quantum computation. Okay, now let me just very briefly explain you how you can actually show that any fermionic non-Gaussian state is a resource for match-gate computation. First of all, you notice that this state here, which is also a 4-qubit state, is very similar to this M state, and what you can use this state for is to realize a phase gate. Okay, so this would be an entangling gate, which was also a resource, so this would allow you to do universal quantum computation. Now, just as a remark, for 2 and 3 fermionic states, they are always Gaussian, so they can never be a resource, because 2 and 3 partite fermionic state you can always generate with the free resource, with match gates. Okay, so they can never be a magic state. So the smallest number of parties that you need is 4. And for 4, you can show that they are all equivalent up to some match gates. Okay, so you can always map one into the other, which is if it's a fermionic non-Gaussian state. And then what you can show is that if you have more parties, so k parties, fermionic state, which is non-Gaussian, then you can always find appropriate measurements on this state that leads to a 4-qubit state, 4-partite state that is fermionic and non-Gaussian. Hence, you have that this is a resource. And in this way, you can show that all states that are fermionic and non-Gaussian are actually resources for match-gate computation. So what I've explained so far is that these match gates are interesting because they allow you to do even a compressed quantum computation, which of course nowadays might become more and more interesting because these are the devices that we have at our disposal now. We are probably quite far away from having such a huge quantum device, but the small ones we have, and so we can use that to simulate quantum computation if they can be decomposed into match gates. And on the other hand, we know that if you have just match gates at your disposal, then there is a simple way to lift this to get an as powerful device as a universal quantum computer by just adding any kind of pure fermionic non-Gaussian state. Okay, so this makes this universal. Now you can go one step beyond that and ask, okay, so if I have now these magic states, when is the system still simulable? When can I still do the computation classically as efficiently as on a quantum computer, and when does this break down? And this is similar to what has been shown for Clifford gates, where you consider various different input states, so for instance, product states or computational basis states, and you allow or don't allow for adaptive measurements. Okay, and depending on that, you see that you can have a classical simulation, or you actually really get something as powerful as a universal quantum computer, which is many of us believe that you cannot simulate it classically efficiently, hopefully. Okay, and you see, for instance, that if you have product states, this allows you, in this setting, allows you to have the T state, which is a magic state. And if you allow also for adaptive measurement, then we just discussed that this leads to universal quantum computer, Hence, you have this result. Now, if you do the same thing for match gates with the same input states, then this gets very boring because everything remains classically efficiently simulatable, basically. What you have to do instead is to look at the input state, which is now the analog, the counterpart of the input states for Cliffords, which are the magic states that we just discussed. So if you vary this, then you see that you get actually exactly the same picture as what we have for the Clifford gates. Okay, so if you have this is the result that I was just explaining. Magic state plus adaptive measurement allows you to do universal quantum computation. However, if you restrict to either just match gates but no adaptive measurements, or the other way around, then you can still simulate that classically efficiently. Okay, this brings us to the next topic, which is, of course, you might also want to know. Okay, so I was talking about pure states only. So what happens now if we have mixed states? Can we do some kind of distillation? And this is a current project that we're working on, where we want to see how can we go from some mixed state row into, how can I transform that with just using the free resources, so match gates, how can I then transform this into a magic state? Okay, now let me, in the last 3 minutes that I have, just explain very briefly something about the verification and validation of quantum computations. So when we talk about verification, there are various different notions of verification. One is the verification of the output of a quantum computer that we actually don't trust. Okay, so the scenario that people consider there is that you are a user of some device. It might be some cloud computer, so this is not in your hands, but you can use that very powerful tool, this quantum device, and you want to use it in order to carry out some computation. And so this works that you're sending some kind of problem to this quantum computer, and the quantum computer does the computation and then sends you back the answer, yes or no. Now, the question that was posed many, many years ago is that how can I verify the answer? Okay, so if I send a problem to a quantum computer that I cannot compute myself, okay, so I'm far away from being able to compute that because I just have a classical device, and then I get an answer, and this is a yes or no, how could I possibly check whether this answer is true? And so this sounds actually like something that is probably not doable, but actually very recently, Umila Mahadev, in a very nice result, has proven that you can actually do that. So you can, with a purely classical verifier, you can check the outcome and you can get confidence that the outcome is indeed correct. This is based on some computational assumption, namely on the existence of the so-called post-quantum functions, like this learning with error functions. Another approach here is that you have the same problem, but you allow for a very small quantum device. And with this, it has already been shown many, many years ago that you can also verify the answer of the quantum computer. And this is actually information and theoretically secure. Now, another kind of idea of how you, or another approach, or what you want to verify is a quantum device where you have access to this device, or you trust the person that is operating it. Okay, and then, as we all know, I mean, there are many, many, many proposals of how you can verify that, going from state or process tomography to randomized benchmarking and so on. And there are some recent very nice proposals which allow you also to compare two different quantum devices. So to these different experimental setups, you can compare and relate them to each other with just classical communication. Okay, so what I would like to now talk about very briefly is a different approach where you actually use some old result due to Martin van der Nest, who proved that if you have a circuit that is composed of match gates and also these Clifford gates, but in a way that you, for instance, have first all the Cliffords and then all the match gates, or the other way around, and then you make a measurement of a single qubit, then you can actually simulate that classically efficiently. Okay, so whatever these gates are, as long as they're just match gates and then Cliffords, or the other way around, then you can simulate it classically efficiently. And that's a very nice result because you can use that, for instance, to construct what we call the validating circuits, where imagine that you have here some circuit that is now composed of whatever, Cliffords and match gates and whatever, and you do a computation that you cannot simulate classically efficiently anymore, simply because this device is already too large. Okay, and then you do some measurement at the end, but you have no idea of how you can estimate the error here. And so one way of maybe getting some insight into the power or the correctness of this computation is to simply change the order of the gates. So you keep the same number of gates, also the complicated ones, you keep the same number of the complicated gates, but you reorder them in order to have such a setting where you have first just match gates and then just the Cliffords, and then you make measurements in order to obtain the results. And then this is something that you can classically actually efficiently simulate. And some other approaches actually using these magic states that I was just explaining before for match gates, and this is actually based on highly motivated by some paper by Richard Joser and Sergey, where you can actually show that you can construct with the help of these match gates and also with this idea of these match gates and Cliffords a circuit that you can classically efficiently simulate, and that is close to your actual circuit. And with this, I would like to thank my collaborators, Richard Joser and people around him, and in particular Martin Himstreit, who is here, who just finished his PhD. He was involved in the many projects that I was talking about. Mark Langer, who is a master student, is now working on the purification, and Antoine Neven and Jose Kraus, who are working on the verification of quantum computation. Thank you for your attention.
Okay, great. Thanks very much, Barbara. That was a fantastic talk. I'm going to go straight over to questions from the audience. The first one of which is, are there any qubit platforms where match gates are easier than other types of gates that you know of?
Yeah, so okay, so I cannot say with certainty now. I mean, I remember giving once a talk about match gates, and some experimentalist was approaching me, telling me exactly that, but I cannot say more now. No, sorry.
Okay, okay. Let's see, the next question from Annette Messenger is, are the swap gates necessary for universal quantum computing only if the qubits are limited to nearest neighbor interaction in a 1D chain? How is it in higher dimensions?
So no, the swap gates are not necessary, they are sufficient. So you can add many other gates like the Hadamard gate or something like that, and they do also make it universal. So there are many gates. You see that it's like with Clifford. So if you add somehow something that is not a match gate, then basically it gets universal. Okay, I see. You add many gates.
I mean, that was sort of related to a question I had as well. I was curious as to these special, well, okay, these special states you require. You said you used the term non-Gaussian, and I wondered if that. You know, what's the origin of calling it that? Is it anything to do with their phase space representation?
Very good. Thanks for the question. Yes, I mean, I completely skipped that because out of lack of time. But indeed, I mean, there's a mapping between, and this is also why we call it fermionic and non-Gaussian, because you can view that as a fermionic system, and then indeed the match gates are just the Gaussian operations. So if I say non-Gaussian, I really mean that you cannot generate it by just applying Gaussian operations to the state, to a computational basis state.
Okay, okay.
Exactly, but there's a strong link between the two, yeah, fermionic systems and match gates. Okay, great. And yeah, there's time for one more. So from Ryan Mann, who asks, does applying the compression to get a log n size circuit give an alternative classical simulation algorithm to that of the FKT algorithm? Sorry, FKT algorithm? Yes, that's what he's asked. Perhaps, yeah, I'm not sure what that acronym stands for. Perhaps that's something that can be taken up in the Slack channel. Sounds like a few more, a bit of elaboration on that question might be necessary. Okay, with that, I'll thank you again, Barbara, for that lovely talk.